Hello and welcome to this IOP video about potential dividers aimed at Key Stage 5 teachers. It is the first of a two-part session on potential dividers and electromotive force and internal resistance, but it is recommended that you watch this one first. Before we teach our students much about potential dividers, we need to be really comfortable that they can use the equation V equals IR and rearrange it happily. They need to be able to measure potential difference and current for any components in a circuit and use that to calculate the resistance. So what is a potential divider? Well, we often think of it as just a couple of resistors in series with each other in a circuit. It could be 3, 4 or more resistors as well. One that students are likely to meet is a rheostat, which is also a form of potential divider, but we'll come to that one later. We're going to teach potential dividers in a very particular way. There is an equation that can be used to solve them, but that's not what we're going to begin with. We're not even going to begin by deriving that equation. We're going to just see if our students can spot the pattern. And if we get them to a position where they can just recognise the pattern and understand how the potential difference changes, then this is going to set them up for later calculations involving light-dependent resistors, thermistors, and other qualitative calculations. So this is an activity that I usually run with students on whiteboards. So I'm drawing it on my whiteboard in big, and the students are holding up little whiteboards with their answers. We're not going to do that today, but that's what I want you to picture about how we are going to teach it. And the very first thing I'm going to ask them to do is to draw a circuit with 2 resistors in series. So students probably draw this one most often. They often also draw this one or this one. They're all the same. I think it's a slightly eccentric person that's going to draw one like this, and the less said about this one, the better. But overall, they're all fundamentally the same diagram. For today, we're going to draw our potential divider this way up. And the reason why we're going to do that is because it makes everything simpler if all of my students are drawing it the same way up. This is how I would teach it with students. Each time I'm going to change the resistances and I'm going to ask students to guess what the potential difference will be. Now, at first their guesses might be fairly random, but eventually they're going to spot a pattern, and it's that pattern that I really want them to recognise for themselves. So let's start off. Picture we've got a 6 ohm resistor and another 6 ohm resistor. Now each time we're going to ask our students, what is the potential difference at the top? What is the potential difference across the bottom resistor? That might be called the voltage out or the voltage across the top resistor, or different words. But each time we're asking the same question, can you make a good prediction? Now if you need to pause to have a think, then just have a pause now. If you said it was 6 volts and 6 volts, you were right. And this is it acting as a potential divider now. We've got a 12 volts input from the battery and we've got 6 volts and 6 volts coming out. Now, let's change it. We've now got 3 ohms and 9 ohms. Pause, have a think. Excellent. And hopefully you thought it was going to be 3 volts and 9 volts, but a lot of your students are going to think it's going to be the other way around. They might think it's 9 volts and 3 volts. But it doesn't matter if they get it wrong. You can run as many of these as you need to until they spot the relationships that you need. Hopefully this one is now straightforwards. Pause if you need to. Four volts and 8 volts are what we get out. So always adding up to 12 volts. Let's make it a little bit harder. So what about 4,000 ohms and 8,000 ohms? Pause it, have a think. The answer is still 4 volts and 8 volts. We've got a really interesting situation now. The resistance isn't the thing that tells us what the potential difference we're going to get is. Changing the resistance doesn't affect the potential difference that we get out. It's the ratio of those resistances that's the thing that affects the potential difference. Okay, in this situation with 4,000 ohms and 8,000 ohms, we're going to have a lower current than we did on the previous version, but in terms of the potential difference, the result is the same. So we've shown how you can use this with students. You can keep using as many examples as you need to until they've properly understood all of your messages. In this example, you're trying to demonstrate that the exact numbers don't have to add up to 12, the ratio is what's important. And in this example, the students will probably try to solve it exactly, but actually they can learn more just by spotting that overall it's going to have potential differences of 0 and 12. All of those have been relatively nice numbers, and that's deliberate. I chose 12 volts as the input voltage because I know that that's going to be easy to work with, and I've chosen other numbers that work well as well. But what if we get a harder sum? So what if the numbers on the resistor were instead 23.4 ohms and 41.9 ohms? I hope we all agree that we're not going to be easily able to do that by inspection as we did some of the other ones. Well, there are a number of ways that you can do it. I'm going to start by trying to figure out what the current would be in the circuit. So the current, which is the potential difference, divided by the resistance. At this point here, it's going to be 12 divided by the total resistance, which is 23.4 plus 41.9, and that is equal to 65.3 ohms. So if we do, the current is 12 divided by 65.3 ohms, we can figure out it's 0.184 amps. Now, it's really handy having the resistors at the top and at the bottom because I can refer to them like that. So let's figure out what the potential difference is going to be across the top resistor first. So the potential difference on the top one is the current times the resistance at the top, and that is 23.4 times 0.184, and that gives us an answer of 4.30 volts. The potential difference at the bottom is, well, it's 12 minus 4.30, so by inspection that's 7.70 volts. And by a similar method, we can come up with a general solution. So let's consider that we've got a voltage going in there, we've got a current going round, the current is the same everywhere, which is the voltage divided by the total resistance. So the voltage in divided by the resistance at the top plus the resistance at the bottom. Then we know the potential difference at the top. So the potential difference there is just the current times the resistance at the top. So it is voltage in divided by resistance at the top plus resistance at the bottom, multiplied by the resistance at the top, and the voltage at the bottom is equal to the same current multiplied by the resistance at the bottom. So let's try and see one of the first advantages to solving problems by doing them as ratios first, rather than just solving them by plugging the numbers into the equation. To do that, we'll do a question involving either a light-dependent resistor or a thermistor. Instead of trying to solve a problem with numbers, what happens if instead of the numbers we were told that one of these resistors was actually a thermistor? So we've now got a fixed resistor at the top and we've got a thermistor at the bottom. What will happen, for example, to the voltage if the temperature goes up? So before we do that, we might need to remind ourselves that there's a graph for thermistors which says as the temperature goes up, the resistance goes down. So that's the graph for most thermistors. So as the temperature goes up, what's going to happen to the resistance? Well, the top resistor resistance doesn't change. So as the temperature goes up here, the resistance of the bottom resistor is going down. Now, if the top resistor is unchanged and the bottom resistor is going down, if our students have understood this as being a series of ratios, they will be able to say that the voltage will drop at the bottom here and the voltage at the top will therefore go up. Now, this is really handy if we're trying to figure out, for example, how to set up some air conditioning or some heating. If the temperature goes up, the voltage goes up. So we could use the top circuit to switch on an air conditioner. Similarly, at the bottom, as the temperature goes up, the voltage drops. So this could be something that, for example, turns off the heater, so is connected to a heating circuit. Note, in a real-world circuit, those red wires wouldn't be connected directly to a heater, but they would be connected to a transistor which could then turn on or off a heating circuit. Up until now, we've said that a potential divider is just a couple of resistors in series, but actually it can be a whole series of resistors, or we can use one of these, a rheostat, as a form of potential divider. Let's have a look at how we would draw that. Sometimes you'll see a potential divider drawn like this, where you'll see a single long resistor and an arrow going in towards the centre. But the truth is, what's effectively happening is you've got a fixed resistance here, but it can be thought of as two resistors, one at the bottom, one at the top, and we're joining in to the middle. And as you move it around, you're shrinking and growing the different resistors above and the different resistors below. Here is a rheostat. Along the bottom, we've got this long fixed resistor. Connecting across the top, there's no resistance in that wire, but then we can connect anywhere along that fixed resistor. So what does it look like if we were drawing the circuit diagram? Well, it's a fixed resistor along the bottom, and then we've got an arrow coming in wherever we like. Rheostats are really useful in experiments because not only can you easily adjust their resistance, but also, even when they get quite hot, they have a very constant resistance. So let's try now attaching this rheostat to a power supply, or in fact in this case some batteries. So it should be approximately 6 volts, the potential difference across the full resistor at the bottom. And if we then attach a multimeter here so that we can read the voltage, the potential difference across from here down to here, we should be able to vary the potential difference. So effectively we've got 0 resistance here, and we're getting almost 0 potential difference, and as we increase it, move across, we should get to the full potential difference. And we can add another voltmeter onto this side. So now we're looking at it, we're looking at the potential difference across here. And hopefully you should see that these two numbers will add up. So 0.22, 5.3, 4.9, 0.6. These two numbers will add up to make the total potential across the whole thing. Students will need to be able to work out that a couple of resistors in series becomes a potential divider, but they may also be expected to use it in different situations as well. So for example, the rheostat we used, if we are successful in getting them to spot this relationship, the pattern of the ratios between the two resistors, then they are really well equipped to handle qualitative problems involving thermistors or LDRs, for example, and they'll also be really well set up to understand electromotive force and internal resistance.